Hello, my name is Zachary Williams, and today I will be presenting the NBA MVP using machine learning algorithms to predict future MVPs. So to jump right in, some of the stuff we're going to go over, we're going to go over the motivation for the project, why I chose this project exactly, the objectives of the project overall, and then to get into the nitty gritty of the project, we're going to be going over the data and method overview, the results from all of the analysis that we did, the conclusions that we take from those results, what might come in the future, and then go over some references and special considerations and thank yous. So dive right in. I'm going to talk about the motivation for this project. So my why for this project is how I like to put it. There are two different reasons why I wanted to tackle this. One is that I love basketball. The season starts today. Today is October 24th. And it's by and large my favorite sport, and I love the statistics of basketball. I love the community. They're constantly trying to create new and different ways to measure player performance, and so I find that basketball statistics are fantastic to work with. They're not as advanced as the NFL's or football in general, but I think that's good in a sense because I think it gives us sort of some wiggle room to try and experiment with different statistics that might be able to better understand player performance overall. And so I wanted to take a shot at taking some of these basketball statistics and grow it into something greater and create a predictive model for the MVP. And then, as I said, basketball is by far my favorite sport. Been playing it since a kid. I've loved them. I love basketball since then. So I wanted to do a project that integrated that a little bit more. I also work in the sports betting industry, and so it's sort of a perfect triangle of connection for me for this project. The second reason is that I wanted to create a project that was informative and impactful. Now, something people could look at, understand, and interpret, and then create their own judgments based off of it. Whether that be player performance, betting on the sport itself, just argumentative for conversation. But I also wanted to create a project that could grow into something much greater than it is now. I hope over the next year that I'm able to develop some more fine-tuned things, understand the data a little bit more, try different things to try to understand awards betting in general, which I'll dive into a lot more later in the presentation. And so the main idea for doing a project like this, where we're predicting something in the future, is that it's informative and impactful now, but it can grow over time through integration of new basketball statistics that appear as well. So that's my why for this project. I'm very happy about it. I'm very excited to show you what results we got later on. So a little bit about the objective we're trying to do. So there were three objectives when we started. One was figuring out what statistics are best for predicting who will win the NBA MVP. We dive into those very statistics later on in the results section, but that was one of our objectives because we wanted to figure out why exactly, or what made an MVP an MVP. What sort of measurements are there out there that are best at predicting who the MVP will be in any given season? And we accomplished that. As I said, we're going to go over that in the results section a little bit more, but we were able to figure out what features most affected the awards race for the NBA MVP. So that's fantastic. The second objective was to take the findings from the prediction models and compare it to major sports betting markets. I was very vague about what sports markets we were going to, or sports betting markets we were going to do. We focus on one and their fake numbers because we couldn't find them for the 2022-2023 season. So while they're fake numbers, they're relatively close to what we would have seen last year, just based on some prior knowledge that I had about the markets in general, how the awards sort of shook out and what the end of the regular season last year looked like. But we were able to accomplish that. We were able to do a comparative analysis on the sports betting markets and the prediction models. later on in the presentation. And like I said, we're going to dive really deep into it in the results section. The third objective, one that I knew going into it, we weren't going to be able to figure out until probably a month after the project was due. Who will win the MVP 2024, this upcoming season, the 2024 or 2023-2024 season. Obviously, as I mentioned, the season starts today, and so we have no data to work on. So about a month in, we'll have good, concrete, and enough data to add to our data set, run through the models, and be able to predict the 2024 MVP before it is actually announced. And the plan is to run that month over month or bi-weekly to show how the MVP race has changed based on the model over time, and how the betting markets have changed with the model or without the model, depending on how well the prediction's working or not. So obviously, we're going to keep working on that. And I'm really excited about the next month or so, fine-tuning that and figuring out exactly what works. So moving forward, let's talk a little bit about the data we're talking about. So obviously not all of you are basketball fans, but that's okay. This project was meant to touch two different demographics in terms of who will understand what they're looking at. One was the data science community, and the other was the basketball community. I wanted this project to be able to talk to both and for both to understand what they're looking at. That was sort of my audience approach to this all. And so to give you a little bit of context about what we're looking at, I'm going to talk about the data that we used and go into a little bit of detail about what it means. So before running the models on the data, we wanted to look at what exactly an MVP looked like in the NBA. Were there certain benchmarks that a player had to hit to become the NBA MVP? This is going to change a little bit this season because they instituted new rules. But since those new rules are only for this season and not for the previous 10 seasons that we studied from 2013, 2014 season to last year, we're going to go off of these parameters that we have set so far. So I created a checklist to becoming the NBA MVP. So to quickly go over it, a player must play over 48 games. They have to score more than 13.5 points per game. They have to average more than 30 minutes per game. They have to have an overall team standing of over 16th. And what that means is that there's 30 teams in the league. If a player is on a team that's worse than the 16th ranked team, then they are eliminated from the data set. Number 5, we have to average more than 1 assist per game. The player also has to average more than 3 total rebounds per game. I say total because there are offensive and defensive rebounds. So add those together. That's your total rebounds per game. They have to have over 3 of those. Number 7, we have a field goal percentage of over 37% per game. And then number 8, attempt more than 10 shots per game. Doesn't matter what kind of shots. Could all be 2-pointers, could all be 3-pointers. As long as there's 10 per game, you're good. And number 9, have a player efficiency rating over 18. We'll get more into that number a little bit later as I'm talking about the model and what exactly we had to deal with. And so those are our 9 points in figuring out who could win the MVP. No modeling involved. As I mentioned, there are certain rules going in this year that are important and that I've actually included in the dashboard as a KPI, key performance indicator. But we have a parameter, play over 48 games. Players actually have to play over 65 games this season in order to win the MVP. It's just a new rule that they instituted to try to mitigate people resting as much as they do. It's been a broader problem in the NBA over the past few years, and they're just trying to get rid of that problem by incentivizing awards by playing games. And then another key data manipulation point that I wanted to make was how we were dealing with NAs. There's some players who have zeros just because they didn't attempt a 3-pointer or didn't register a rebound or something like that. there were quite a few zeros. So there were a couple different ways that we approached that. One was that we removed the NAs outright. The players weren't necessary for the model to begin with. And so we just took the players out who had those zeros, or who had those NAs, excuse me. The second way was that if we needed the data point, we replaced it with a 0 because we assumed that the player just did not register that stat during the season. And like I said, some players just don't attempt 3-pointers. And so that's going to affect some statistics. Some players didn't make a free throw, all that kind of stuff. And so that's a little bit of how we manipulated the data for this problem. So to go into the data a little bit more, we have 5 different data sets that we're working with. One that deals with per game statistics, so how many points, rebounds, assists, a field goal percentage a player averaged per game during each season. Then we have advanced statistics, which goes into a little bit more of the development of statistics in the basketball community. A lot of these take our per game and total data and per 100 possessions data, which is a metric that the community loves to use to measure on a level playing field each player, and converts them into digestible and effective data points, I should say. And then we also take into account the team standings, as we mentioned, so how well a team performed that season. Statistics from 538 called Raptor. They are a measurement that measures against box score and on-off plus minus, and then considers pace of play and other things to measure player performance, and inevitably comes out with a stat that's called WAR, wins above replacement. We're going to get into a lot of that more later. To make a quick note on Raptor, they actually sunset this data as of last year. So this data, while it proved pretty effective for the model, it wasn't the best at predicting, and so I'm not super mad about having to take it out. But it was a great statistic, and I'm sad to see it go. But unfortunately, it's being sunset by the company who created it. So I will probably take it out of the model in future iterations. And then finally, our benchmark, MVP voting, which is based on MVP voting share. And I wanted to get a little bit into the weeds on what that meant. So MVP voting share is based on a couple different things. To start, the MVP is voted on by media members in the NBA community. That could be prominent podcasters, prominent TV members, prominent radio hosts, prominent writers, you name it, they're there. They all have a ballot. They each pick who comes first, second, third, fourth, and fifth in the MVP race. And then each place has a point system associated with it. So first place gets a certain amount of points, second place gets a certain amount of points. Those points are then all added up and then divided by the total points that you could earn if you earned all the points. So you can actually see in the picture in the bottom right, Kevin Durant in the year 2014 season earned 119 total first place points. That means out of all the points available for first place, he earned 119 of them. Points total won, or I'm sorry, he earned 119 first place votes. Those votes then correlated to 1,232 points won. Divide that by the total amount of points that you can have, which is 1,250 in that year. You get a percentage share of 98%. That's how MVP voting works in a nutshell. So we can move past all of this data and go to our full data set, which was all those data sets over 10 years from the 2013-2014 season to last season, into this big data set with over 5,000 rows and 63 different variables. We then take that data, institute our benchmarks that we mentioned a couple slides ago, and we get this reduced data set that's much more manageable for the models to use and is much more informative and accurate when predicting MVP share. So as you can see, there's 227 rows instead of 5,219 rows. And we eliminate some columns that are either duplicates or don't really matter and won't be needed. So yeah, that's the data in a nutshell. Next, we're going to move on to any mathematical and analytical details that we need to discuss that were used in the project for predicting the MVP. So a few of them I want to go over. The metrics I use to measure how the models performed, and then feature impact. R squared was used and mean squared error were used to measure how effective the models were. So R squared, obviously, it is 1 minus sum of squares residuals divided by the total sum of squares. And then mean squared error is 1 over the number of observations times the sum of observations, where I is equal to 1, times y sub I minus y hat sub I squared. Those metrics are presented in the Tableau dashboard that I'm going to show you later. So I won't go too much into detail there. And then select k-best is a metric that sklearn has that is great for parameter impact metrics, how well a parameter affects the model, essentially. Charts we used. Model performance is one of the dashboards that I'm going to talk about later. Player by player breakdown is another one. But model performance uses tables, bar charts, and scatter plots to accurately display the data. Player by player breakdown uses tables and scatter plots with filters. So here, there's a little bit more user interface with that one, as the other one's a lot more informative and you can't really play around with too much. And then we dive into regressors. I used 4 different ones. Obviously, some worked better than others with the data, but I wanted to make sure that I was able to test a bunch of different ones and being able to figure out which ones impact the data the most, and then to sort of showcase that for this project, I show an average of all of them and compare it against betting markets, which I will show you later. So obviously, support vector regression, something that maximizes relationship between input and continuous target variables, while also minimizing prediction error. This was the best performing one, and I think it's because it takes into consideration minimizing the prediction error. SVR tends to weight more towards that than any of the other models. And so I think it's important to point out that, because I think that's why SVR was the better model. Random forest regressions, they fit a number of classifying decision trees, various subsamples of the data set, and then uses averaging to improve the predictive accuracy and control overfitting. Basically, it is a regression model that takes a bunch of different samples of decision trees for classifiers to improve predictive accuracy and not overfit the data too much. Gradient boosting, something new that I wanted to try for this project, didn't come out as well as I wanted it to. I think it was the weakest regressor. There's 2 reasons for that. One, it might be that my hyperparameters were poor because it's the first time I've used it, and I don't think I know the best fine-tuning parameters for it, but I'm gonna keep working at it in the future for this project, and so I'm excited to see what the future holds. Basically, gradient boosting is a collection of weak regression models combined to produce a strong predictive model. And then finally, we used k nearest neighbor regression models to measure the data, or to regress the data, which are just a regression model that uses local interpolation of the targets associated with the nearest neighbor, uses clustering to regress data, essentially. So that's all the math and analytical details for this project. The results are presented later on in the Tableau dashboard. So I talked a little bit about why I chose certain things, but I'm going to go into a little bit more detail about it. So why I chose 4 different regressors instead of just the one that performed the best. It was sort of part of the project. I wanted to see which one worked the best and then use and showcase them against each other to really drive home the point that they all work relatively well, just some work better than others. We chose these regressors because I felt that they best fit the data, essentially. It was a lot of different variables that they had to take into consideration. And so I thought clustering would work well for K&N because of the wide variety. I thought SVR would be just great because it mitigates risk. Random forest would be great because it takes a bunch of different decisions into effect. And then gradient boosting was something new that I always heard was great, and I wanted to see if I could make it work. The evaluation stage, we used R squared and mean squared error because they're both just great for measuring performance for regressors. And then I used select K best because it was a pretty simple metric for measuring feature importance and impact. And so I went with that. It was quick to throw into the code and figure out exactly how well each feature affects the data. So that's where we went there. And then charts, I wanted them to be both comparative and descriptive because I want people to be able to quickly look at these charts, understand what is happening in the background, and understand what the results mean in the greater basketball and data science community. So the overall analysis. I'll dive into this a little bit later, but I wanted to quickly show you guys what the Tableau dashboard and some of the results look like. So this is our first page, the model results and performance. So essentially what this is showing you is the mean sum error or mean squared error for each model. So as you can see, support vector regression worked the best out of all of them, then random forest, then K&N, then gradient boosting. And as I mentioned before, K&N and gradient boosting I had lower hopes for, but I feel like I can improve at least gradient boosting, maybe not K nearest neighbor, just because it might not be the best regressor for this. But fine-tuning some parameters to better fit gradient boosting to the data might be an effective way of doing that. It's the first time I've used it, so I'm kind of excited to dive back into the code and figure out exactly how we can improve those performances. But to accurately display to the data science and basketball communities that this is how well we're predicting MVP voter share, it was important to include this data. So that's where it is right there. Obviously, R squared, closer you are to 1, the better the model. Mean squared error, closer you are to 0, the better the model. So that's sort of how those metrics work. Next, we dive into model results. So it's important to note here that our model didn't actually predict the MVP correctly. This was expected going into it because there's a human element to voting for the MVP that I discussed a little bit. A lot of media members do it. And so there's a lot of bias towards certain things that data can't exactly predict. One thing is that before last season, Nikola Jokic had won the MVP the previous 2 years. So there's a concept called voter fatigue where they won't vote for the same person over and over again, even if they are the best candidate, like our model shows you. So in real life, Joel Embiid got 91.5% of the first place votes. Nikola Jokic got about roughly 2/3 of the rest of them, 60% for Giannis. And then Jason Tatum got 28%, and the rest are pretty much negligible. Our model actually came back with Nikola Jokic winning the MVP, Joel Embiid coming in the close second, and Giannis coming in close third. So our model predicted a much closer race, but that was expected because I think there were outside factors from the data that affect this, and something that I'm going to approach and talk about later on how we can sort of take into consideration this fact. But yeah, the model results came back, we came back really close to what they actually were. So that's fantastic. We love to see that our model was almost as accurate as the real life results. And then, as I mentioned before, our next chart is going to be games played. This will be more impactful for the new season, just because that minimum that I talked about is 65 games needs to be met by players who are going to be considered for the MVP. So you can actually see the 5 vote getters in our model. Only 3 of them would be eligible this year to win the MVP, top 3. Whereas Giannis, who came in 3rd this year, would not have been eligible. He would have been 2 games short. But yeah, that talks about that a little bit more. And then feature impact, how well each feature affected it. These are the top 5 results. VORP, which is something I'm going to talk a little bit more in detail on the next slide, as well as these other metrics. This is box plus minus, player efficiency rating, win share, and WAR. And then finally, we look at the chart on the right, and it's MVP odds based on a sports book. And obviously, as I mentioned, they're fake. Couldn't find the real MVP odds from last year. So we are going to see that Anthony Davis, who is at the bottom, has about a 10% chance of winning the MVP based on the model predictions, and have positive 2,500 odds to win the MVP based on sportsbooks. The more negative the number, the higher chance that player is going to win the MVP based on the betting markets. So as you can see, MVP for last year, Joel Embiid, who ended up winning, had the best chances of winning the MVP based on the sports books. Nikola Jokic coming in 2nd, Giannis in 3rd, Jason Tatum in 4th. But what this chart shows you is that it's probably more likely that Nikola Jokic should have won the MVP that year based on solely data statistics that I discussed earlier in the presentation. So that's sort of what this dashboard shows you. These are the results we got from our model, an average of all of them, all of the results thrown in here, games played, which will come into effect next season, feature impact, which is super important, and then how all this data compares to sportsbooks. And then as we move to the second one, we go to a player-by-player breakdown. So this chart will effectively show us how each player performs on that chart that I showed you before, and then give you individualized results for each player. So as you can see, for Jason Tatum, his MVP odds are at 1,500, positive 1,500. His SVR prediction was around 20%, 21%. His random forest prediction was around 14%. Gradient boosting at 28%. K nearest neighbor at 7%, and an average of around 20%. And you can see that in the chart here. It's just at about 20%. And then it gives a little information about the player's season so far. So we see per game statistics, advanced statistics, and as we mentioned, we see player efficiency rating in here. We see win share per 48 in here, usage percentage, which is super important statistic that the community uses. And then our feature impact values. So I thought it was important to show what each player was achieving in these key areas that are presented in the model results of performance that are key metrics. So we see that players of VORP of 5.1, BPM of 5.5, so on and so forth here. And then that's all charted. What's great about this page is that we can take any of these players and figure out all these statistics for them. So let's take the Bam Adebayo player. You see that everything adapts. So you see the MVP odds shift down for him. His SVR score lowers. He does get some love from some of the other models, but on average of 0, essentially. And then you see all these stats show, and you can see that these values are significantly lower than Jason Tatum's in each one. So that's the results in a nutshell. And so some key takeaways we can have from that are that our SVR models, as I mentioned before, return the best MSE, and R squared scores. Then random forest comes in a very close second, and then KNN and gradient boosting are essentially tied for third. And so if we were to use this sort of stuff like in the real world, we would just stick with SVR. It fits the data best, and so we're just going to use it to predict. That's going to be our best indicator of how well we can predict the data. But since I wanted to showcase all four, I thought I would just stick with them throughout the project. It's important to note that the models and the real results don't match, and that's okay. They were really, really close, and still I think that means that our models work, and we can use them for future reference and be able to predict future MVPs using these models, even if they're not as predictive as we would like them to be. One of the things that I'm going to plan on doing in the future is go back to the 2013-2014 season, predict that season MVP based on the rest of the data, and then work my way back up to 2022-2023 and see if all the results are effective for each year. So that's something that we're going to be able to do to validate how well the models perform, which wasn't able to get to it for this project. As I mentioned before, the 5 best models for, I apologize. The 5 best features for predicting the MVP share were value over replacement player, which is just a box score estimate of the points per 100 team possessions, not player possessions, that a player contributed above a replacement player, translated to an average team and prorated to an 82 game season. It's a lot of information that I just threw at you. Just understand that the metrics basically measuring a player against an average player on an average team for an 82 game span. And then box plus minus, how well a player performs on the court versus off the, or how well a team performs when a player is on versus off the court. It's an oversimplification of it, but that's what that means. Player efficiency rating is a measure of per minute production standardized such that the league average is 15. So league average player has a value of 15. Anyone above league average player, over 15, below, not below average players, under 15. That's how that metric works. Win share, how much a player contributes to winning. And then wins above replacement, how well a player performs over a replacement player. Those all sounded kind of similar, and they are in effect, but the math behind them is a little bit different, where you get some things take into consideration pace of play, some things don't. But those were our 5 best features for predicting the MVP. All right, so our conclusions. We have a few of them. As I mentioned a couple times now, SVR over everything. I think it was the most effective regressor because it prioritizes mitigating risk and mitigating error. And so that leads us to believe that essentially it performed the best because it's mitigating the most amount of risk, which is somewhat like sports betting, I guess, in a sense. Were our objectives complete? Obviously, I completed 2 of them. We figured out what best features work, and we figured out, well, not figured out, but we compared it against MVP betting odds. Obviously, our 3rd objective is a work in progress, and we won't be able to do it till around probably the end of November, is when we'll have some good data. But yeah, our objectives were 2/3 complete, a third on the way. And then our model, another takeaway was that our model didn't exactly match real outcomes, and that's because of the human element of it all. But they came really close, and I'm really proud of that fact. Next, we have newer data that's better for prediction. Some of the more advanced and newer data in the community is performing a lot better at predicting the MVP than older, more traditional data. And so that's important to understand as we move forward with the model, is that some of the older data isn't really great at predicting the MVP. And then some pre-processing improvements that I can make on the back end. There were certain standardizing issues that I ran into, and I think there's a better way to institute standardization for the data. I just don't know it yet and can't wait to tackle it. But use a standard scaler, which is standard. But I think there might be better ways to approach the data pre-processing. But those are our 5 major conclusions from this massive project. So finally, what comes next? So first, code cleaning. My code's a mess. I need to clean it to be able to do more stuff with it. So first things first, after this project is to tackle code cleaning, clean up the code, make sure it works well, it runs more smoothly. New data, as I mentioned, come mid to late November. We're going to have data for the 2023-2024 season, and I'm super excited about that. I can't wait to run the model against something that doesn't exist, be able to actually predict something that does not exist. And so I'm super excited about that. Future enhancements for the future, or future enhancements. New ways that we may be able to consider the human element that I've mentioned that I think affected the model and wasn't completely accurate. One way that I've already thought of is doing sentiment analysis on some of the podcasts and some tweets, on some news articles, and being able to run sentiment analysis on each of those and see if people are talking positively, negatively about the MVP against a certain player. It'll be a lot of web scraping, but super excited to try it. And then other statistics that might pop up that are viable for predicting the MVP might come around, or I might be able to find through the community and stuff like that. So next, other sports. Can we institute what we learned in this project and be able to apply it to baseball, to football, to hockey, to golf, to tennis, to any sport, and predict who's the best at each of them? I say best because not every sport has an MVP. The 4 major ones do. Soccer does. I know. Tennis, I am actually not sure. But in any case, can we learn, or can we take what we learned in this project and apply it to other sports? And then predicting other years, as I mentioned, I want to go back to 2013-2014 season, run the regression models against that season, and then work my way back up, see how well the model predicts other years. I just didn't have the time for this project. And then other awards. Can we do awards like Rookie of the Year? Can we do Offensive Player of the Year, Defensive Player of the Year? Can we even maybe predict who's going to be on the first team All-NBA, second team All-NBA, third team All-NBA, and so on? And see if this data and the regression models are great at predicting that. But obviously didn't have enough time. This is like 6 months to a year worth of work that I am super excited to dive into. This is a project that I've been waiting for a very long time to try. I am super excited I was able to tackle it for this class, and I can't wait to do some of these other things in the future on it. So I wanted to shout out a couple people in my life who were great at helping me with this project: Kaylee Campbell, Ben Kling, and Kyle Larson, someone else in our class. They all helped with some coding that I was having trouble with, and some of the conceptual understandings of both basketball and machine learning. So that concludes this presentation. I had a blast figuring out and running all the code, setting up the Tableau dashboards, being able to conceptually understand how the data works for this and if it's great at predicting the MVP and not. And we figured out that it's actually pretty good. And I cannot wait to institute this into this upcoming season, which, as I mentioned, starts today. I'm very, very excited. So I thank everyone for listening, and I hope you had a great time.